Think about it. They're everywhere. In your phone, in your remote, your car, batteries are the silent, portable powerhouses of our entire modern lives. But if you ever really stop to wonder what's actually going on inside one of them, well, today we're going to crack one open, figuratively of course, to really understand the chemical magic that makes our world tick. You know, if you look at a cross-section like this, it doesn't seem like much, does it? Just some layers of metal and this pasty stuff inside. But packed inside that humble little container, there's a super carefully controlled chemical reaction happening, turning chemical energy into the electrical energy that powers up our devices. It's literally a tiny, self-contained powerhouse. And that's the big question, isn't it? How do you take a raw chemical reaction, something that would normally just fizzle and give off a little heat, and how do you tame it to produce a steady, useful flow of electrons? To get our heads around that, we've got to start by looking at what we're trying to tame in the first place. Right, so before we can understand how a battery controls a reaction, we first need to see what happens when that exact same reaction just runs wild. You know, what if we just mix the key ingredients together and see what happens? So let's set the stage with a classic chemistry experiment. We're going to take a solid strip of zinc metal, and we're just going to drop it into a solution that's full of these blue copper ions. This very reaction, by the way, is the one that powered one of the first reliable batteries ever made, the Daniell cell. And boom, this is what happens. It's totally spontaneous. It just goes all on its own. The zinc metal immediately starts to dissolve because it's giving away its electrons. At the same time, the blue color of the solution starts to fade because those copper ions are grabbing the electrons and turning into solid copper metal. You can actually see it plating right onto the zinc strip. It's a direct, powerful, and very fast exchange. But here's the catch. While there's a ton of energy being released here, we can't actually use it for anything. The electrons are just jumping directly from the zinc atoms over to the copper ions. All that amazing potential is just wasted. It just bleeds off as a tiny bit of heat. I mean, you can't exactly plug your phone into a beaker of slightly warm water, can you? So how do we wrangle all that wasted energy? Well, we have to stop the electrons from making that direct jump. We need to force them to take the long way round, through a wire. And the amazing device that pulls this off is called an electrochemical cell. And the core idea behind it is, honestly, it's so simple, it's brilliant. You just physically separate the two halves of the reaction. This kind of reaction is called a redox reaction. That's just a fancy term for any reaction where electrons get transferred. So if you can build a device that keeps the electron giver separate from the electron taker, you can control the entire process. Okay, let's do it. Let's build one of these cells right now, piece by piece, so we can see exactly how each part helps us harness that power. All right, we've got 4 essential parts. First, we need 2 separate beakers, or half cells, to keep those chemicals from mixing. Then we pop in our electrodes, the strips of zinc and copper metal. This is where all the action happens. Next, we connect them with a wire on the outside. This gives you electrons a highway to travel on. And finally, the secret ingredient, the salt bridge. Now, this little guy is absolutely crucial. It completes the circuit by letting ions move between the beakers, which keeps everything electrically balanced. Seriously, without it, the whole show would grind to a halt almost instantly. And there you have it, the whole setup. Working together, you can literally trace the path. See? Electrons leave the zinc electrode, they travel up through the wire, maybe through a light bulb or a motor, and then they go down to the copper electrode. Once they get there, the copper ions in that solution grab them and become solid copper. It's this beautiful, controlled, continuous flow of energy. Okay, time for a couple of key terms we need to know. The anode and the cathode. The electrode where oxidation happens, that's the one losing electrons, is called the anode. In our battery, that's the negative terminal. And you can see it actually loses mass over time as the metal dissolves. The other one, where reduction happens, the gaining of electrons, is the cathode. That's our positive terminal. And it does the opposite. It gains mass as new metal gets deposited onto it. Now, I know that can be a lot to remember. So here are 2 super simple tricks that chemists have used forever. Just remember, ox, anode is oxidation, and red cat, reduction is at the cathode. Anox, red cat. Simple, right? But trust me, it works every single time. Okay, so we've built our cell, we know the path the electrons are taking, but why? Like, what's actually pushing them along that wire? What is the driving force that makes them want to go from the anodes to the cathode in the first place? This is my favorite analogy for it. Just picture a waterfall.
Water only flows downhill, right? That's because there's a difference in height, a difference in gravitational potential. Well, it's the exact same idea for electrons. They flow from the anode to the cathode because of a difference in electrical potential. The anode is the top of the waterfall. The cathode is the bottom.
So that height difference in our electrical waterfall has a technical name. It's called the cell EMF, or electromotive force. And we measure it in something we're all familiar with, volts. The easiest way to think of voltage is as the electrical pressure that's pushing the electrons through the wire. A higher voltage means a bigger waterfall and more energy from each electron. And this is the really cool part. There is a simple rule that tells you if it'll work. If you do the math and the voltage for the cell comes out as a positive number, that means the flow of electrons is going to happen all by itself. It's a spontaneous reaction, just like water always flowing downhill. That positive voltage is basically the green light telling you, yep, this reaction can power a battery.
All right, that was a lot of chemistry. We've gone from a messy splash in a beaker to a controlled flow of power. But let's bring it all back home. Why does this matter to you and the battery in your pocket? So, at the end of the day, what is a battery? Here's the deal. Batteries are just incredibly elegant energy converters. They take the raw power of a chemical reaction that really wants to happen anyway, and by cleverly separating the parts, they force all that energy to travel through a wire as a flow of electrons. And that directed flow of electrons, well, that is electricity. That's the magic that's running your phone right now.
And hey, this isn't just some abstract theory. For that specific zinc-copper cell we've been talking about, if you build it under standard conditions, it's going to give you a steady 1.10 volts every time. It's a predictable amount of electrical pressure from that specific chemical combo. Different chemicals, of course, give you different voltages. And that right there is what brings us to the future. The basic principle we've just walked through is actually over 200 years old. But the search is constantly on for new chemical reactions, new combinations that are way more powerful, lighter, and more sustainable. The next generation of batteries, from what's in our phones to what's going to power our cars and our cities, it all operates on this same fundamental science of the electron waterfall. The real question now is, what amazing new materials are we going to build the next ones out of?